Hello, today I will be working out one example. So, once again I am repeating. Hello, in last lecture we have discussed the design procedures and the different codal provisions on gantry girder. We have seen how to step by step design a gantry girder. Today we will go through one workout example through which we will understand how a design can be made for a particular case. So, let us go through that example. Design a gantry girder for a mill building to carry an overhead travelling crane having the following data, right. So, crane capacity, so let assume crane capacity as say 190 kilonewton, and weight of crane excluding the crab is equal to say 150 kilonewton. So, weight of crane is 150 kilonewton and weight of the rail, this is say 0.2 kilonewton per meter, and span of the crane between rails say 14 meter, right, and minimum hook approach so this will be say 1 meter, let us consider, and wheel base is 3 meter, and span of girder is given say 6 meter, right. And another thing, height of the railway section into 70 millimeter, and assume Fy say 250 MPa and E value let us assume 2 into 10 to the power 5 MPa. So, these are the data we have, right. So, what we have seen that crane capacity is given 190 kilonewton, weight of the crane excluding crab or trolley weight has been given 150 kilonewton, then weight of the trolley 60 kilonewton, weight of the rail 0.2 kilonewton per meter, span of the crane between the rails, this is given 14 meter, and minimum hook approach is 1 meter, wheel base 3 meter, and span of the gantry girder is 6 meter, right. So, if we draw the diagram of the gantry girder, we will see this span is crane span is 14 meter, right, and weight of the crane excluding the trolley, that is 150 kilonewton, and the crane capacity has been given just 190 kilonewton. So, this is 190 kilonewton. So, let us put this as A and this is as B, this point, because we will be requiring to find out the moment etc., right. So, what we will do now, we will go for step 1. In step 1, calculate the maximum vertical load, right. So, first we will calculate maximum wheel load, that will become WC weight of the crane, that is 150 kilonewton, and weight of the trolley was 60 kilonewton. So, 190 was the capacity and 60, so 250 kilonewton, right. So, this maximum static wheel load will occur when the crane hook is at a minimum distance of 1 meter, means because crab will be here. So, at a minimum distance of 1 meter it will be occur. I can show here that maximum static wheel load at A will occur when the crane hook is at a minimum distance of A, that is 1 meter, because this is minimum hook approach. Minimum hook approach was given 1 meter. So, the reaction force R A we can find out. One is W c by 2, W c, this is W c. So, W c by 2, because this will be acting at a L by 2 distance, right. So, this will become W c by 2 plus W c into B minus A by B, sorry, W t into B minus A by B, right, because the W t is acting where, somewhere here, right. So, we have to find out the total value as 150 by 2 plus 250 into 14 minus 1 by 14. This is the length of the crane. So, after calculating we will get this kilonewton, that is 307.14 kilonewton. Now, since two wheel loads are at A, so W will become half of this total load. So, W, the value will be becoming half of 307.14, that is 153.57 kilonewton, right. So, in this way we can find out. Then what we will do? We will go to step 2. In step 2, what will be that calculate maximum bending moment due to vertical load. Now, we will calculate the maximum bending moment due to the vertical load, right. Maximum bending moment, again we know we have to find out the position where the maximum bending moment will occur, right. The worst condition we have to consider, right. So, first is static wheel load. Static wheel load is given, say 153.57 kilonewton, and we can add some impact allowance, so 25% additional load, additional 25% of the static load, that is, so 25% means 25 by 100 into 153.57. So, this will be becoming 38.39 kilonewton. So, the total load will become 153.57 plus 38.39 kilonewton. So, this will be the total load. So, this value is coming 191.96 kilonewton, right. Now, wheel base is given, wheel base length, that B is given 3 meter, and span of the girder, span was given 6 meter, right. Now, we have to check whether it is, means where the maximum load will come, that has been given, that whether it is 0.586 L, greater than 0.56 L or less than 0.586 L, right. That we have to check, and accordingly we have to find out, right. So, what is the value of 0.586 L, we have to find out, right. So, 0.586 L will become 0.586 into 6, that is 3.516 meter, right. So, static wheel load we have the total load due to impact, and now we are seeing that B, the base is 3 meter, and we can now check that B is less than 0.586 meter, 0.586 into L meter, because this value is, this is B is 3 meter and this is coming 3.516 meter, 3.516 meter, right. So, since B is less than this, maximum bending moment will occur when center of span is midway between CG of loads and one wheel load, right. Now, so in this way we can make it. I will come with this picture. Hence, the distance of one wheel from center will become half into B, that is half into 3, that will be 0.75 meter. So, let me draw the picture first, then we will understand. So, this is 6 meters. Say let us give the points C and D, right. Say this is the span of the girder. Now, CG distance is here, that means this is 3 meter, this is 3 meter, right. Now, wheel load has to be placed in such a way that the CG of the wheel load and CG of the span will be at the middle of from one load, means from one wheel. Say this is the wheel, right. So, this is 3 meter, wheel base is 3 meter. So, the wheel base CG is here, right, and CG of the span is here. So, the CG has to be middle in between one wheel and CG of the wheel, right. This is the condition where the maximum moment will develop, what we have discussed yesterday. So, this will become B by 2, this will become B by 2, right. So, B by 2 will become how much? Sorry, this will become B by 2. So, this will become B by 4 and B by 4. So, B by 4 will be becoming, B is 3 meter by 4. So, 0.75 meter. That means, one wheel has to be placed at a distance of 0.75 meter from CG of the span. So, this is the 0.75 meter, right. So, if we keep this, then only we will get the maximum bending moment, and W we have calculated the two base load means two wheel load is calculated. This is 191.96 kilonewton and this is 191.96 kilonewton, right. So, in this way we can make it. Now, other things we have to calculate. So, this is how 0.75 meter has come, right, and other thing is that this will be half of half, right. So, now if the self weight as we have considered earlier, that is 2 W by 250. So, 2 into W was given, W we have calculated here. So, from this we can find out 2 W by 250. So, that is 1.535 kilonewton per meter. The self weight has been assumed as per the discussions in earlier lecture. We have seen that will be 2 W by 250. So, W has been calculated earlier. So, from that we can find out the self weight. Self weight means approximate self weight of the girder, that is 1.535 kilonewton per meter, and weight of rail also let us assume that say 0.2 kilonewton per meter. Weight of rail we are assuming 0.2 kilonewton per meter. So, the total UDL load will become W1 plus W2, that is 0.2 plus 1.535, that is becoming 1.735 kilonewton per meter, right. So, the usual load we are going to get 1.735 kilonewton per meter, that is throughout the girder it is there. So, another load will come into picture like this, that is 1.735 kilonewton per meter, right. So, this is another load. So, this will be the position of vertical load for maximum bending moment. Right. So, position of vertical load for maximum bending moment. So, this is how we can find out. So, that we have drawn here, that again I am just repeating that here W will be 191.96 kilonewton, the wheel load, similarly here 191.96 kilonewton, and this is 1.735 kilonewton per meter, which has been calculated, and this value is 0.75 meter, and this is again if we calculate this will be also at 0.75 meter, and this will become 2.25 meter, right. So, this is the diagram we can have. Now, what we will do? We will calculate the maximum bending moment. So, maximum bending moment will occur in this way. So, first to calculate the maximum bending moment, we have to find out if this is C and if this is D, we have to find out the reaction forces here, then we can find out the value. So, what will be the reaction forces? Say RD, RD will be what? So, to find out reaction forces at D, let us take moment about C. So, then what will happen? RD into 6, RD into 6, right, will be equal to, see, RD into 6 will be equal to this all loads, we have to take moment about this, right. So, RD into 6 equal to 1.735 into 6 WL square by 2 into 6 into 6 by 2, this is 1 plus plus 191.96 into 0.75 plus 3.75. How it is coming? See, 0.75 is this one, for this load this is 0.75, and for this load this will become 0.75 plus 3, so 3.75, right. So, taking moment about C, we can find out RD into 6 equal to this. So, from this I can find out RD, RD value will become 149.175 kilonewton, right. And similarly, RC I can find out now. If I take moment about D, we can find out RC, which will become 1 by 6, similar way 1.735 into 6 into 6 by 2 plus 191.96 into 2.25, one another will be 5.25 from D point. So, this is becoming 245.15. Otherwise, we can make summation of V, means summation of F V, right. That summation of F V means the total load along vertical direction. So, we know total load is this one plus this into L. So, that minus R D will become R C. So, this way also we can find out. So, total load on the girder we can find out that will be becoming basically RC plus RD, that will be 149.175 plus 245.15, right. So, if we add, this will become, total load will become 394.325. So, this is the total load on the girder, right. Similarly, we can find out the moment. Now, maximum moment we can find out. So, the moment we are going to get the total load, we can find out maximum moment. Maximum moment will be how much? That R d into 2.25, because maximum moment will develop here, right. So, R d into 2.25 minus W L square by 2, 1.735 into L is 2.25 by 2. So, from this I can find out maximum moment as 331.25 kilonewton meter. So, in this way we can find out maximum moment. How we found? The reaction force at D we know. So, R d into that distance where the maximum moment is coming minus the downward load, that is W L square by 2, right. So, in this way we can find out the maximum moment, and where the maximum moment will occur, that we understood now. The position how it has been made, now I think we have understood. So, we will go to step 3. In step 3, we will select a suitable section, right. That means, to select suitable section, what we will do? Sigma B t will be 165 MPa, we will assume. Sigma B t we will assume 165 MPa. Okay. So, we can find out Z required. Z required will be m by sigma B t. So, m maximum moment we already found 331.25 kilonewton meter, that is 331.25 kilonewton meter into 10 to the 6 will become Newton millimeter by 165. So, this will become 2007575.7 millimeter cube, right. So, the required Z we have. Now, as you know, we have to increase little higher section, because finally we have to find out a composite section, means combined section, right. And also the sigma B c value will be less, because the beam is laterally unrestrained. So, from compression point of view, it will not be safe if we consider the same. So, now we will increase, say 15% let us increase. So, Z will be 1.15 into Z required, means 15% we are going to increase. So, this will become 2308.7 into 10 to the power 3 millimeter cube. Okay. So, now what we will do? Now, let us see what type of section we can use. So, let us use IS, means I section let us use. Say with this Z value, if we go through the SP6, we will see that ISWB 600 may be one of them which we can try. So, let us try with ISWB 600 at 133.7 kg per meter. So, these sections we are going to try, where Zx is equal to 3450 into 10 cube millimeter. You see that we have taken a little higher side, because as we know that we have to check lot of things. We have to check not only for bending stress in tension, but also for bending stress in compression with unrestrained laterally unrestrained. Then again combinedly with the horizontal load, vertical load plus horizontal load, that also we have to check. Then again shear stress we have to check. So, once if we take a little lesser value, means little close to the required value, then it may not be safe. So, here for the sake of making safety, means to make all the things safe, let us consider little higher value, so that all the things will be under safe, right. However, for practical purpose of design, we can check with a lower value whether it is okay or not, to save the economy, means to make the size economy. Next, what we will do? We will find out other values like Ixx, that is 106198.5 into 10 to the 4. So, from SP6, the structural handbook, we can find out the required value of the section. So, Ixx is there, which is given, Iyy is given 4702.5 into 10 to the power 4, this is 10 to the 4 millimeter to the power 4, right. So, this has been also given. Other things are like area of the section has been given 17038 millimeter square. D, the depth, overall depth is given 600, because ISWB 600 we are using. B is given 250 millimeter, right. And TF, the thickness of flange, TF, that is given 21.3 millimeter, and TW is given as 11.2 millimeter, right. Also, we have to provide a channel, and as we told that if I section is having some B width, then channel depth has to be little higher size and around 50 millimeter higher, as we told earlier. So, considering this into mind, let use say ISMC 300, say at 35.8 kg per meter. So, what we did, that as the flange width of the I section is 250 mm. So, at least we should choose ISMC, means channel section 300 mm, because flange means channel section depth has to be at least 50 mm higher than the width of the flange of the I section, right. So, if as width is 250, we are going to consider 350. So, this is 250 and this is 300. So, 50 mm higher we are making. So, from this again we can find out Ixx for channel section, that will be 6362.6 into 10 to the 4 millimeter to the 4. This is given, right. Similarly, Iyy C, that is given 310.8 into 10 to the 4 millimeter to the 4, and Cyy for channel, that is given 23.6 mm, and thickness of wave of the channel is given 7.6 mm, and area of channel is given 4564 millimeter square. So, these are the value which are given in SP6 we need for the calculation of the combined properties, right. Like Ixxc means the moment of inertia about xx of the channel 6362.6, and Iyy is 310.8 10 to the 4 millimeter to the 4, Cyy that is 23.6 mm, and thickness of wave is given 7.6 mm, and area of the channel is given 4564 millimeter square. So, with this now we have to calculate the neutral axis of the combined section, neutral axis and the moment of inertia and other things of the combined section. So, what will be the combined section? How it look like? Say this is the I section we have chosen, right. This is the I section. Then we are providing channel section, sorry, right. This is the channel section which is placed at the top. Now, we know all the dimensions of the I section as well as the channel section. So, this is 250 and this is the thickness of the flange, that is given 21.3 mm, and then thickness of the wave also is given, that is 11.2 mm, right, and this total distance is, this is 600 mm, right, and this is 300 mm, and now other things are like this depth, wave, thickness of the wave of the channel, that is given 7.6 mm, right. So, with this we have to find out the neutral axis, right. So, neutral axis we will find out now. Yes, this is gantry girder, right. So, neutral axis we have to find out. Now, overall depth how much it is coming here for the section? Overall depth will be 600 plus 7.6, that is 607.6. Now, we have to find out the neutral axis depth. Say this is neutral axis depth, say this is y bar, the distance from top flange to the neutral axis depth, right. So, this we have to find out. Now, this is placed, remember, the centrally, that means it will be 150 and this will be also 150, placed centrally. Okay. Now, so what we will do? We will calculate the neutral axis and moment of inertia. Okay. So, if we see, the y bar will become area of channel into CYY, right, because we know the center of gravity of the channel is CYY, CG distance, then plus area of wave into h by 2, h is the depth of the I section, plus TWC, TWC means thickness of the wave of the channel, right, by A plus AC. A is the area of the channel, AC is the area of the channel and A is the area of the I section. So, how we are getting that? We are taking moment about this. So, if we take moment about this, what will happen? Total area into y bar is equal to this area of channel into its CG distance, and then area of wave, area of I section into its CG distance, that is 300. CG distance will be 300 from top and 300 from bottom, but from top, because of presence of channel, it will be 300 plus 7.6, right. So, 300 plus 7.6 means, okay. So, now if we make, this is 7.6. So, area of channel section into its CG distance 23.6, which is given, then area of I section, right, into CG distance, that will become 300 plus channel. So, this one, and the area has been divided. Now, from this we can find out y bar as 247.6 mm, right. So, y bar is becoming 247.6 mm. So, how do we get? I think it is clear to you that we are taking moment area about this, about top flange, right. Then we are getting the neutral axis of the combined section. So, from here it is 300, now this is 247.6. So, we can find out this value also, right. So, this value will become, now we can find out that 607.6 minus 247.6, right, because total depth is 607.6 and neutral axis from top is 247.6. So, this will be neutral axis from bottom will be this one, right. So, that we can find out. Okay. So, y t will become, means from tension side, that will become 600 plus 7.6 means 607.6 minus this. So, this will become 360, right. So, this is becoming 360, right. So, this is called y t and this is called y c. Y t means the in tension zone and y c is in compression zone, right. The depth of the neutral axis in compression zone means this one, and this will be the y t for tensile zone, right. So, in this way we can find out the neutral axis. Now, we can find out I x x, right. I x x will be how much? Moment of inertia of the combined section. So, if we calculate moment of inertia of the combined section, what will happen? That if we see here, this is the I section and another is gun edge, sorry, this is I section and this is channel section. So, when we are going to find out moment of inertia about the combined section, what will happen? This is the neutral axis shifted from here because of combined action. So, because of shifting, what we are doing? I x x will be I x x about its own axis plus area into r square, means shifting, because of shifting. This is the r value will become how much? 307.6 minus 247.6. How? If we see the diagram, this is 307.6. This total distance, if we see, this total distance is 300 plus 7.6, that means 307.6, and this is 247.6. So, this distance will become 307.6 minus 247.6. So, shifting of moment of inertia from neutral axis of its individual to neutral axis of the combined one. So, for that we are making in this way 307.6 minus 247.6 whole square. So, I x x equal to I x x dash plus a r square. Okay. So, this is the moment of inertia about the C G of the combined section due to the I section. Similarly, due to the channel section, this is the due to the channel section. In case of channel section, we have to see this is the I and that will be I y y, right. Whatever I y y will be here I x x. So, 310.8 is the I y y value of the channel section that has been taken, because I x x is generally taken in this way, I y is taken in this way. So, as it has been rotated, so I y will become I x x and I x x will become I y y. So, I y y plus area into r square means just shifting, because shifting is, we know the C G distance of the channel section. Suppose C G distance of the channel section is here. So, because of shifting we know, so total minus this will become r square, right. So, 4564 into 247.6 minus 23.6 whole square. So, this will finally become 112332 into 10 to the 4 plus 23211 into 10 to the 4 millimeter to the 4. So, if we add, finally we will get 135543 into 10 to the 4 millimeter to the 4, right. So, Ixx we are getting, Ixx means Ixx of the combined section, right. So, step 4 is over. Now, we will go for step 5. In step 5, what we will do? We will find out the stress, that is bending stress, bending tensile stress, and we will check for that, right. Bending tensile stress we know, we can find out sigma BT cal. Sigma BT calculate will be mx by Ix into Yt, right. Yt is the distance from CG of the combined section to the extreme fiber of the tensile zone, right, Yt. So, we can find out, that is 331.25 into 10 to the 6 by Ix, that is 135543 into 10 to the 4 into Yt. Yt is 360 that we found earlier, this 360 Yt value, right. So, from this I can find out the value as 87.98 Newton per millimeter square, which is less than 0.66 Fy, that is 165 MPa. So, as it is less than 0.66 Fy, we can say this is safe. So, from bending tensile stress point of view, the chosen section is safe. Next, what we will do? Next, we will go for compression one. So, for compression one, what we will do? We will determine the sigma BC for the whole section. Now, this is a new thing which we have not discussed earlier. New things means we have not worked, means we have not done any example through this, means how to find out sigma BC. Why? Because this is not only the beam is unrestrained against its lateral direction, but also the beam is not symmetric, the cross section of the beam is not symmetric. So, because of that we have to find out from the formulas, right. In case of equal flanges with unrestrained beam, we have the tabular form results in the IS code in table 6.1 to 6.1a to 6.1f, but in this case we have to find out. So, for that let us see. So, for whole section, first we will find out say IY. Okay. IY means we have the section and we have the channel section. So, IY in this direction let us find out. So, what will be in this direction IYY of I section, that is 4702.5 into 10 to the 4 plus IY of means Ixx of channel section, right. So, simply because CG of the combined section is not going to change along y axis, in y direction CG of the combined section is not going to shift. So, simply the summation of the two I means two section of I values can be made. So, this is becoming 11065.1 into 10 to the 4 millimeter to the 4, right. Now, IY of the compression of the flange about YY of the whole section. Now, again we will find out the IY of the compression flange, that is we know this is I section, this is neutral axis, right. So, we will find out what is the IYY value of this compression flange. because that is required also, as we have seen yesterday, this value is required to find out the stresses. So, Iy in compression flange. So, that will become how much? Half of 4702.5 into 10 to the 4 plus 6362.6. 6362.6 is this one, and half of the I section. So, this is becoming 8713.85 into 10 to the 4. So, Iy in compression flange is becoming 8713.85 into 10 to the 4 millimeter to the 4. Now, what we have to find out? We have to find out the ratio of the moment of inertia of compression flange alone to that of the summation of the flanges. So, that omega will become Iycf by Iy. So, Iycf is 8713.85 into 10 to the 4 and Iy is 11065.1 into 10 to the 4. So, the ratio is becoming 0.788. The ratio is becoming 0.788, right. So, on that ratio we can find out from table 6.4 of IS 800/1984 the value of K2. Now, value of K2 against this omega can be find out from table 6.4, which is given 0.288, right. So, this has been given. Now, Ry we can find out. Ry is Iy by A, and Iy and A are already calculated. Iy was calculated as from this formula Iy, that is 11065.1 into 10 to the 4. So, Iy is 11065.1 into 10 to the 4 and area is total area of I section plus area of channel section. So, square root of Iy by A is equal to becoming 71.57 millimeter, right. So, the Ry, radius of gyration about y axis, we are going to get as 71.57 millimeter, right. Now, assuming the end of the girder to be restrained against torsion, but no lateral restraint, that means for that L will become, this effective length will become the total length, that is 6 meter, okay, because we have to find out the slenderness ratio L by Ry. So, the moment we find out the slenderness means effective length, we can find out the slenderness ratio as L by Ry. L is 6000 millimeter, Ry is 71.57, right. So, we can find out the value lambda as 83.83. The slenderness ratio now we are finding out as 83.83. Now, as we know Yc is 247.6, that means Yc which one? That if we draw the combined section, this is Yc and nothing but this is called in code as C1 and this is Yt as C2, right. So, C1 is given as this value, C2 is given as this value, right, and from that we can find out psi as 1, right. If we see the table in IS code, we will find out the K1 value as 1, right, and this Y value which was given in the formula, that 26.5 into 10 to the 5 by L by Ry whole square. So, that also we can find out from this formula as this, right. So, Y is getting as 377.1 and overall depth of the section, as we have calculated, overall depth of the section will be 600 plus the wave thickness of the channel, that is 7.6. So, that is 607.6 millimeter. So, overall depth of the section we have 7.6 millimeter. Now, we have to find out the mean thickness. Mean thickness means, you see, we have a thickness here, the thickness of the channel, and again here the flange means thickness of wave thickness of the channel and flange thickness of the beam, this I section, right. So, when we are going to find out a mean thickness, what we will do, that you see the area is 250 into 21.3, this is 250 and thickness is 21.3, and this area is the wave of the area of the wave of the channel is 300 into 7.6, this is thickness of the wave of the channel, right. This is depth of the channel, this is width of the flange, and this is thickness of the flange of the I beam, right. So, by total is 300, because this is total 300 into T. So, in this way we can find out the mean thickness as 25.35. Why this is required? This is required to calculate the value of x, right. So, x can be find out as like this, y into root over 1 plus 1 by 20 into L by R y into T by D, right. So, T by D whole square. So, if I put the value, y we have found 377.1 into square root of 1 plus 1 by 20 into L by R y we found already into T, T is the mean thickness which we have found out here, by D, D is the overall depth of the combined section, that is 607.6. Now, calculating these values, we are getting the value of x as 478.73, x as 478.73. So, the elastic critical stress FCB can be found now, which is K1 into x plus K2 into y into C2 by C1, right, K1 into x plus K2 into y into C2 by C1. So, if I put the value K1 as we got 1, x we got already 478.73 plus K2 we got 0.288 and y we got 377.1, then C2 and C1 we already got, C2 as 360 and C1 as 247.6. Now, putting this value, we will get the value of FCB as 853.96 MPa. So, now again T by TW ratio will become the this 25.35 by 11.2, that is 2.26, right. So, FCB should not be increased by 20% because of this. So, sigma BC can be calculated from this formula, that is 0.66 into FCB into Fy by FCB to the power n plus Fy to the power n whole to the power 1 by n. So, in this way sigma BC can be found. So, what will be the sigma BC? That is 0.66 into FCB value is 853.96 into 250 by FCB 853.96 whole to the power 1.4 plus 250 whole to the power 1.4 whole to the power 1 by 1.4, which is becoming 146.68 MPa, right. So, we are getting sigma BC value, that is permissible bending stress in compression, as 146.68 MPa. So, what we will do now? Now, we will go for step 6 to check compressive stress, permissible bending compressive stress. So, bending compressive stress will be mx by Ix into Yc. Now, mx is 331.25 into 10 to the 6, Ix is 135543 into 10 to the 4 into 247.6 is Yc. So, this is becoming 60.51, which is less than sigma BC, because sigma BC value we got 146.68. 146.68. So, from compressive stress point of view also the section whatever we have chosen is okay. Next, we will calculate the bending moment due to horizontal load. So, bending moment due to horizontal load, that will be F h equal to 1 by 10 into 60 plus 190, so 25, and W h will become F h by 2, that is 25 by 2 is equal to 12.5. So, the arrangement of wheel load for the maximum bending moment due to horizontal load should be the same as that for the vertical load. Means the whatever arrangement we have done for vertical load, the same arrangement will be working for the horizontal load to get the maximum bending moment. So, we can find out the maximum bending moment, and for that we can find out the horizontal reaction force RH, that will be simply 1 by 6 into 12.5 into 0.75 plus 3.75 is equal to 9.375, right. So, RH we got. Now, what we will do? Now, My we can find out from this, that is 9.375 into 2.25 which will be equal to 21.1 kilonewton meter. Now, we can calculate the compressive stress due to horizontal loading. So, we know IYCF. So, we can find out sigma BC cal horizontal, that will be My by IYCF into HC by 2, that is 331.25 into 10 to the 6 by 135543 into 10 to the 4 into 300 by 2, which is coming 36.66 MPa, right. So, now what we will do? We will check for the combined, means for vertical load and for horizontal load, what is the stresses are coming, that stress has to be less than 1.1 sigma BC as per the Codal provision as we have discussed earlier. So, sigma BC cal vertical and sigma BC cal horizontal is becoming 60.51 plus 36.66, that is 97.17, and permissible value will become 10% more than the calculated one. So, 1.1 into 146.68, so that is becoming 161.348 MPa. So, this is becoming 97.17, so hence it is safe. So, now we will calculate the stress due to longitudinal force. So, due to longitudinal force, FLH will be the 5% of the total wheel load. So, 0.05 into 2 into wheel load 191.96. So, this is becoming 19.196. Similarly, MLH will become FLH into HR plus YC. So, this value will become 6.096 into 10 to the 6 Newton millimeter, right, where HR is the height of the rail, right. So, we can find out the stress in longitudinal direction from this formula, FLH by A plus MLH by IX into YC, and we will find the value as 1.99 MPa, which is very small, as we told that this stress is becoming very small. So, next in step 11 what we will do? We will check for shear, and because of shortage of time I am not going to calculate that. You can do as I have discussed in last lecture, check for shear stress, then the pitch of the rivet, that also we can find out, right. So, with this we will get the pitch, just I am showing the pitch can be find out as this. Pitch will become, if you calculate, you will get maximum permissible spacing is 12 into T, so 91.2. So, we are providing 25 PDS in 2 rows at a staggered pitch of 90 mm. As I told, the example is very big, so it is difficult to complete in one lecture. However, I hope you have understood the process, and the remaining 2 steps if you do at your own you will be able to do. So, with this I like to conclude today's lecture. Thank you very much.